Hi, today we're going to talk a little bit more about power series. We just found intervals of convergence, where we started by finding the radius of convergence with the ratio test, and then we checked the endpoints to get the interval of convergence. We're going to do that same thing today, except we are going to talk about the derivatives and the integrals of power series and what are their intervals of convergence. And it sounds like it might be ridiculously difficult, but we're going to make it pretty easy here. Okay, so when you take the derivative, you can think of it in one of two ways. You can take the derivative term by term, or you can take the derivative of the formula. In either way, you're going to get the same result. And really, you should be able to do both. So let's look at this formula of the given power series. When we take the derivative, first of all, if you take the derivative and the term has a negative, the negative just kind of stays put, right? You don't change that part of the terms, right? Which means negative 1 to the n plus 1 just stays. This makes my first and third and fifth terms negative. So right here, that negative sign is not going to go away when I take the derivative. I still need my first term to stay negative. So I'm going to just put that alternating portion, the negative 1 to the n plus 1, in my derivative. Now think about what a derivative does. When you take the derivative of a power, we're using the power rule, the n plus 1 is going to drop down to the front, and then it's going to decrease. Well, when I drop it down to the front, it's going to cancel with the n plus 1 that's on the bottom. So what I should be left with is just x minus 1, but since I have to decrease the n plus 1, it goes down to just n. So negative 1 to the nth power times x minus 1 to the n. Now, if I shouldn't have really made this. It looks like it's on top. It should be. It should be all, just, I don't have a numerator and denominator anymore. I canceled. So let's make that negative 1 to the n plus 1 here. All right, so if I went about it term by term, and if I were to plug in 0 and 1 and 2 into this new formula, I would get these terms that I'm getting ready to make. But I'm just showing you that you can integrate it, or you can differentiate it term by term. So what is the derivative of negative x minus 1 over 1? All right, so it's negative. We know that. The derivative of x minus 1 is just 1. And think about it. When I plug in 0, I'm going to get a negative sign from here. And I'm going to get something to the 0 from here, which gives me just negative 1. All right, so then let's take the derivative of my next part. It's positive. The 2 comes down and cancels with the 2 that's already there, and I get x minus 1. The next one, it's negative. The 3 comes down, cancels with the 3, but it changes to a 2, x minus 1 squared, plus x minus 1 cubed. Right, the 4 comes down, cancels with that 4, but then it decreases and becomes a 3. All right, and you can kind of check. When I plug in 4 into my new formula, it's going to be, when I plug in 3 to my new formula, this is going to make it positive because I'm going to get negative 1 to the 4th, and this is going to make it x minus 1 cubed, which is what I have. So there's the derivative of a power series going two ways, differentiating the formula and differentiating the terms. Similarly, we can go about getting the second derivative. Okay, the second derivative, I'm going to do the same thing. One thing I have to adjust, and this isn't a huge deal if you were to not remember this, because you would just have one term that didn't really work out. I need to change my n to 1 now, and I'll show you why. All right, when I drop down my n now, I get n times x minus 1 to the n minus 1, right? That's just my good old-fashioned power rule for derivatives. The n drops down, and then I decrease it by 1. Now, this is why we had to change our starting value to 1 down here, because if you try to plug in 0, that just wipes out the term, and our first term doesn't really exist. Going term by term, we should get 1 minus 2 times x minus 1 plus 3 times x minus 1 squared, and so on. And that's what I would get. from plugging into my current formula. All right, it's going to start out positive because when I plug in 1, I don't plug in 0 anymore. When I plug in 1, I get negative 1 squared. Then I get 1 times x minus 1 to the 0. Then I get 2 times x minus 1 to the first, and so on. All right, the integral. It's just going to be going the opposite way. All right, starting with the formula, I integrate it, and I have to start this one at 1 as well, and you should see why in just a second. When I integrate it, I'm going to get negative 1 to the n plus 1. That's just my alternating portion. I'm going to get x minus 1 to the n plus 2, because I increase my power, over n plus 2, because when you take the integral of x cubed, you get x to the 4th over 4. So whatever I increase to here, I also put here. And then I already had an n plus 1 on the bottom. All right, so for the sake of time, I'm not going to write out those terms. You could write out some of the terms, and you could see that it would be integrating these terms up here to get those terms. What I want to talk about more is the intervals of convergence. Now, I'm going to give you that the interval of convergence for the original function was 0 to 2 and that includes the 2, but it does not include the 0. All right, so this thing converges anywhere from 0 to 2. We could also write it like this. Here's the important fact that's going to make this easier. Rather than doing the ratio test on the first derivative and the second derivative and the integral and checking all of those endpoints, we are going to not have to do the ratio test except once. The rule is this. The radius of convergence, make sure you write this down. Of our original function, which is a function represented by an infinite power series, is equal to the radius of convergence for f prime, f double prime, and the integral. Those are the ones we're going to work with. You could take as many derivatives or integrals of this thing as you want, and the radius of convergence is not going to change. The only thing that might change is the endpoints. So the way we want to organize this is like this. I want to arrange them from least differentiated to most. So I'm going to take the integral of f and put it first, and then start writing it, getting more differentiated. If I take the derivative of the integral, I get back to the function, and then I've got my first and second derivatives. The interval of convergence, I'm telling you, and you could have found it from our earlier this section work, is 0 to 2 with parentheses around the 0. So all that's left to figure out is what kind of brackets and parentheses do I use. All right, is it going to be included or is it not? Here's an important rule. If you have your integral function, first and second derivatives, arranged like this, then here's how we can sum up this rule. The thing about it is, and there's a note about this at the bottom of 622, what it says is, from the example shown, f prime is least likely to converge at the endpoints. In fact, it can be shown that if the series for f prime converges, then the series for f will also converge there, which sums up to this. We're getting 2 stars because it's going to save us a lot of work. What it boils down to is below round parentheses is more round parentheses, which means if in the function 0 does not converge, if I take the derivative, it's not more likely to converge, it's less likely to converge, which means, for me, below round is more round. Right? Does that make sense? And when I say below, I mean in this order. If you arrange it this way, if a function, if the endpoint of the function is not included, then the derivative and the second derivative will not be included either. Okay? Going the other way, above square brackets are, I guess I should say, more square brackets. So this 2, I know that 2 is included in the interval of convergence from my original function. Then I know that 2 is included in the integral. Okay? So go below parentheses, you can fill in parentheses above brackets, which leaves me with 3 numbers to check. I need to plug 0 into my integral. I need to plug 2 into my first and second derivatives and see what they do. Let's start by plugging 0 into my integral. Okay, so here's my integral. Plugging in 0 gives me negative 1 to the n plus 1 times negative 1 to the n plus 2. And on the bottom, n plus 1, n plus 2. I mentioned in class problems with two parts of the term that seem like it should alternate. If those are offset, all that does is make this thing completely negative. It doesn't make it alternate, it makes it always negative. And if it's always negative, you can treat it like it's always positive. It doesn't affect our convergence or divergence. So what I have basically here is 1 over n squared plus 3n plus 2. 1 over n squared converges. This is smaller than that. So this thing converges, which means 0 should be included in my interval of convergence for my integral. So there's one of the 3 I actually had to find out. Now I need to plug 2 into my derivative. So I'll try to do that quickly. Plug 2 into my derivative. All right, well, here's my derivative right here. I'm going to kind of in the margins plug in 2 and see what happens. Okay, so I get negative 1 to the n plus 1, which makes it alternate. And then I just get 1 to the n. So this series is made up completely of negative 1s. Let's see, negative 1. 1 to the n is always 1, so this thing's going to go plus 1, minus 1, plus 1, minus 1. Those are my terms. Those terms do not approach 0. Therefore, this thing's going to diverge by the nth term test, which means 0 is not included in the interval of convergence for the first derivative. Okay? Now our little hint takes over. Okay? My first derivative does not converge at either endpoint, and below parentheses is more parentheses. So I can just fill that one in. All right? So it seems like a lot. If I give you a power series and I say find the interval of convergence, and then I say, you know, that takes a couple minutes of doing the ratio test and checking the endpoints. It seems like a lot of work. Then I say, okay, we'll do that for the integral and the first and second derivatives. It seems like you're going to have to do, you know, that much work 3 times over. But the things that make it not that much work. First big help, the radius of convergence is the same. So if we go from 0 to 2 on one of them, we go to 0 to 2 on all of them. The second big help is this down here. The more, pardon my word, derivatized it gets, the less likely it is to converge. Meaning, below parentheses is more parentheses. And the less derivatized it gets, the more likely it is to converge. So if you can find that crossover point, brackets to parentheses on the way down, you've got parentheses the rest of the way. And vice versa on the way up. All right, so I know that's a lot for this one video, but really it's all tricks to make these problems go faster. So that's the second half of 8-8, and I will see you in class. Way to go, soccer.